Hello, I'm Carlos Budde and I will be presenting joint work with Mariëlle Stoelinga on efficient algorithms to analyze attack trees. Attack trees are very well-known models with a top-down decomposition of an attack where we can have a disjunction, so I can get a PIN for a bank account either doing a physical attack or a crypto attack, and for a crypto attack I need to do 2 steps. These are modular descriptions because we can also refine some of the steps into another attack tree where, for instance, here we need have an order dependence. This has to happen before this. Now, at the bottom of these trees, we have basic attack steps, which are indivisible actions carried out by the attacker. We are able to quantify these basic attack steps, for instance, with the time they take for the attacker to perform it or the cost incurred. Then we can also compute metrics for the attack, which yield key performance indicators for my system, for instance, the minimal time to compromise it. So this is very important information that we can derive from these trees. Now, the thing is that to compute these metrics, we have to know whether we are talking of only static attack trees, so only static gates here, or we also have order dependencies, and whether the structure is a proper tree or actually a directed acyclic graph, where we have shared children among the nodes. So with these orthogonal descriptions, we have different shapes and types of attack trees, and also different metrics. And a lot of algorithms exist in the literature for at least the past 20 years that compute the different metrics for these different classifications of trees. Now, one of the key contributions of this work with Mariëlle is unifying algorithms that compute these metrics for big classes of these attacks in an asymptotically efficient manner. Our approach is formal, so we start by defining what is the syntax of an attack tree. We have the nodes of the attack tree, each of them has a type, and then we have a relationship for the children, which is the parent of who. And from there we have also metrics. Now, metrics are not going to be defined in the syntax, but rather in the semantics, in the formal semantics. So first we begin with an attribution that assigns a value to each basic attack step, its cost or its time. From there we are going to define somehow what it means to compute the cost or time of a full attack based from here. And from there we are also going to define what it makes the metric of the full tree from all of these attacks. So the thing is that defining this on the metrics, we have different semantics for static and dynamic attack trees. So let's take one by one. Let's start from the easier, which is the static attack trees. Here, an attack is just a set of basic attack steps, and we call an attack suite just a set of attacks. So here it's standard to have a structure function that determines whether an attack is successful or not when I evaluate it in the tree. And from here we can define also in a standard manner the semantics of the tree, which are essentially the set of minimal attacks. So an attack is minimal when it is successful and no subset of it is also successful. From here we can also define metrics on these semantics. So this is by Mariëlle's contribution, where an attribute domain is defined as the value where I'm going to map my basic attack steps, and also a disjunctive and conjunctive operator. So many metrics can be defined easily in this way, many important metrics of an attack. And from here it is standard to define an attack metric as the disjunction over the different attacks of my tree of the conjunctions of those attacks. So let's see what I mean here with an example. Let's compute the mean cost of this attack. We have an attribution that assigns these costs to these basic attack steps, and then we are going to apply this definition of a metric where I'm going to calculate the disjunction between this attack and this attack, and for each of the attacks I'm going to use the conjunctive operator. So now I replace these values by their definition and summarize to this final conclusion, which is saying just perform the attack with value 1, that is B, that is successful, and that suffices. So that is the minimal attack cost for this attack tree. Now, this gives us a way to compute a metric directly from any kind of static attack tree. The problem is that first we have to compute the semantics of the tree, which we know can be exponentially large. It's an NP hard problem. Can we do better? Yes, we can. This is a result by Mariëlle in 2006, where the domain has to be a semiring. That means that the conjunction operator has to distribute over the disjunction. If we have that, then we can simply do a bottom-up approach, so we push upwards the values of the attributes of the basic attack steps, and whenever we encounter an AND gate, we use this operator, and an OR gate, we use this operator. The algorithm looks like this, and it can be proved that if we perform it on a tree structure static attack tree, the value that we get is the definition of the metric that we did on the semantics. The very good thing about this algorithm is that it is linear on the size of the tree, not exponential, so this is an excellent result. Now, what happens if the tree is a directed acyclic graph, so we have some shared child? Well, here if we apply the bottom-up approach, we are going to push upwards 3 and 1 here, the minimum is 1, 1 and 4 here, the minimum is 1, and then we're going to add 1 and 1, so we're going to say that the minimal cost of this attack is 2, which is not correct, so we can essentially not do this here. This is well known, we cannot do bottom-up when we have a DAG structure tree. What can we do then? Well, either we go to the semantic definition of the metric, or we can use binary decision diagrams. These are standard data structures to represent Boolean functions, which static attack trees essentially are. They are very well used, for instance, in fault tree analysis to compute the minimal cut sets, and they're extremely succinct. The downside is that they can be exponentially large on the size of the tree, but as we know, computing already the minimal attack is NP hard, so we have no asymptotically better solution. Now, the construction of the BDD that represents a static attack tree is, or fault tree is standard. I'm going to go through it, but essentially it's important only to know that for each minimal attack tree we have a unique BDD. Now, another main contribution of this work is an algorithm that traverses this BDD construction to compute a metric. The gist of the algorithm is to start at the top of the BDD and then analyze the case in which this basic attack step takes place. In that case, we are going to accumulate its cost or time or skill or whatever with the conjunctive operator, and we are going to make a recursive call to the high child of the tree. And in the other case, when we go to the low child, we do not accumulate any cost because we are emulating the case in which this basic attack step does not take place. At the bottom case, so the base case of this recursion, we have the leaves of the BDD. If we reach the failure leaf, then we're going to use the neutral operand, the neutral operator of the disjunction, and if we reach the success, then we're going to use the neutral operand of the conjunction. So let's see an example. Here, to compute the missed cost, we start at the top and we analyze the case in which B takes place. In that case, we have to accumulate its value according to this step over here. We are going to consider also the recursive case in which we go to the high child. The high child is the success branch. Then we apply the neutral element for success, which here is 0. That's that case over here. And we also analyze the case for the low child, which goes essentially a recursive call to WA. Here, we can also expand again. WA is either not doing anything here and failing and going to the neutral element of the 0, which is infinite here, so minimum infinite. Or in case that A takes place, we accumulate its cost over here and we go to the recursive case of C, and so on and so forth until we reach the normal form, which is 1. 1, as you recall, is the correct value of the minimal cost here, which we have found using this algorithm. And we can prove that this always works, so this traversal of the BDD always gives you the value of the metric defined in the semantics of my static attack tree. Now that covers the case of static attack trees. Let's go to dynamic ones. So here there can be an ordering attack, so certain steps have to be taken from left to right order. That means that attacks are no longer just a set of basic steps, but also we may require that some of them take place before another ones. The problem is that we are then able to express contradictions, for instance here, where we want A to be before B and also B before A. Now, to rule these cases out, we are going to define the concept of ordering graph, which essentially transform these requirements of order into a graph. And we are going to say that a dynamic attack tree is well formed when the resulting graph of these dependencies have no cycles. So we're going to rule these cases out, and we're only going to work with well-formed dynamic attack trees. So then attacks here are going to be essentially a restriction of this ordering graph, and this allows us to carry on many of the concepts we had for static attack trees. In particular, the semantics of a dynamic attack tree is also here going to be the set of minimal attacks, where minimality includes both the number of steps in my attack as well as the size of my relation. So the minimal attacks are the least restricted in terms of order. Also for metrics, we essentially carry on the previous concept of static attack tree, but here we add a new sequential operator that is going to take care of the things that have to be carried out in order. So let's look, for instance, at the semantics of this dynamic attack tree over here, where we have an attack that can take place from here without an order, that's why the relationship is empty, or from here, which requires that W takes place before C. Metrics can then be defined, essentially as before, with an extra sequential part, which takes care of these kind of scenarios. Let's compute, for example, the minimal time here for these attributes. We apply this definition, and we divide the case of the left attack, which requires no order and therefore only uses this operator, and the right attack, which requires this order and therefore uses the sequential operator. We replace these values for the definition, and we have the normal form, which is the attack 15, which is essentially going this way because we can carry this out in parallel. That is the fastest attack in this tree. However, again, this requires to compute the semantics, which is exponentially large. We have a better way to do things if the tree is a proper tree. Essentially, we can extend the algorithm we had bottom-up for static attack trees to dynamic attack trees, adding the sequential case. And again, we have a linear algorithm in the size of the tree, which can be proven always correct. Now, if the dynamic attack tree is a DAG, we are in trouble because we know we cannot do bottom-up and there are no BDD structures that take correct order. One possibility is to just use the algorithm for the semantics. Another possibility is a new work by Yu and Xu that work on something called sequential BDDs. Unfortunately, we believe that's quite inefficient, but perhaps there's no better way. Okay, that's essentially it. So what we have presented are different algorithms to compute metrics for different kinds of attack trees, which are asymptotically efficient for the different classes. For static attack trees, we have presented a BDD algorithm that traverses the BDD. I did not mention it, but it's in the paper. You can also use this to compute the k-shortest paths, the k-shortest attacks. And for dynamic attack trees, we have introduced posed semantics and a bottom-up algorithm that resembles very much the static counterpart. So that's all. Thank you, and see you after the talk.